Hello and welcome to this ALINT-PRO tutorial. My name is Brandon, and today I'll be moving away from the block level and going over some chip level constraints available in ALINT-PRO. These commands will be useful not just for improving your linting results, but also for providing a draft for a feature SDC file, perhaps be used later with synthesis and static timing analysis tools. In any case, we can begin a foundation for such constraints here. Starting in our first project, we can see 3 violations involving constraints for our clocks, top-level ports, and resets. These constraints are written using the createClock, setInputDelay, setOutputDelay, and createReset commands. Within these commands, we might have to specify things like the clock period or arrival time of signals, which could be quite tedious, especially within designs incorporating a lot of ports. Fortunately, we have the project.generate.constraints command, which can help us write all of our chip level constraints automatically. At command line, we can utilize the clocks switch on this command to generate those needed createClock commands. Notice I must also provide a file here, which is the file that I currently have associated within my project. Once the command is entered, we can see within this file that it has been updated with our necessary constraints. Notice that despite entering no information on clock period, the tool has inferred 2 different values in our generated constraints. By default, 10 nanoseconds is assumed. However, based off naming conventions, the tool can guess other values, as we see here. We can continue generating some of our other chip level constraints by simply adding additional switches to our command, like so. To complete some chip-wide characteristics, I'll add this delay switch to create input and output delays, and this reset switch, which will generate createReset commands, which is actually an Aldec design constraint, and therefore in addition to the common SDC commands that I've been generating. Running the command, we can see all of the constraints within our file. And looking more at this createReset command, we can see that it does not have any clock switches passed to it, meaning this is an asynchronous reset. In fact, in the case of synchronous resets, a clock switch would be passed here. And in the case of asynchronous with deassertion synchronized, a rise clock or fall clock type switch can be used instead. Now at the moment, I've just generated my constraints, but we can see, based off our clocks and resets viewer, that none of them are actually applied. We can verify this in our synthesis report too, as unconstrained clocks do exist. I must first run the project with my generated file applied. This time, the tool will recognize our constraints file and apply them to our clocks, resets, as well as input and output delays. Once the tool is finished running the design, we can see that not only are our previous violations gone, but that our clocks and resets are now properly constrained. When working with constraints, it is useful to know what the tool sees when it comes to our clocks, ports, resets, and other aspects of our design. Fortunately, many debugging commands exist that provide such information. We can see all of our clocks using the allClocks command or getClocks command. And for even more information on a specific clock, we can use the getClocks command along with report attributes to get some detailed information on the past object. In this case, we can see information such as clock period and whether or not this clock was auto-detected. Of course, these commands are not just limited to clocks, but also work for resets, ports, and even clock domain crossings. Overall, these commands can be used to generate some helpful console output when working with constraints. Now, what I've shown so far covers the basic chip level characteristics. Of course, more exist outside of clocks and resets, so I'd now like to go over one more characteristic that is important when it comes to CDC, and that's clock groups. By default, the tool has built-in detection of clock groups when it comes to some generated clocks. In this example, both clocks are controlled by a master clock, and the constraints file shows constraints only for our clock generator. Currently, one clock passes the master clock through, while the second clock divides the master clock by 2. Despite no constraints for clock groups currently written, we can see from our violations that no clock domain crossing is detected. This is because of our default domain detection mode, considering master shared clocks with division by 2 to some n power to be of the same domain. We can see these different modes by going to our project properties, and under CDC within constraints, we can see our current detection mode. If I set the mode to pessimistic and rerun the project, the tool will no longer consider the two clocks to be synchronous, despite one falling into this proper division. As we can see, with the changed property, the tool will now throw the violation. Similarly, I could have set the tool to be optimistic, in which case, no matter the relation between clocks sharing a master, they will always form a single domain. And going even further than that, the tool could have been set up to simply consider all clocks to be synchronous to each other. Now, of course, that's just how the tool can be set up to detect our clock modes. This behavior can, of course, be overwritten through the use of some more chip-level constraints. To show this off, I'd now like to go over another example involving clock groups using their relevant constraints. In this example, we simply have two different flip-flops that are driven by different clocks. If we know transferring data between these clocks to be safe and that they don't need a synchronizer between them, as is the case here, we can use the setClockGroups command to tell the tool that these clocks fall under the same domain, and not to raise any unnecessary violations. As of right now, we can see such a violation as the tool thinks we are transferring data between asynchronous domains, which is a conclusion based off this project's current detection mode. With the use of this command, however, all these reference clocks within a group can be considered synchronous to each other, which will clear up that violation when ran. Looking more at this command here, we can see an additional asynchronous argument. And this simply states that those clocks defined in separate groups are to be considered explicitly asynchronous. So with the project reran with the proper constraint, we can see that previous violation is now cleared. And that'll actually be it for this intro on chip-level constraints, as well as other additional helpful commands. Of course, many more chip-level design constraints can be applied, such as those for false paths, which prevents timing analysis, or setting up case analysis, which can set up different control modes when it comes to signal selection. Additionally, there's many more ADC commands relating to both clock and reset domains, and those, along with all our chip-level constraints, can be found here within the command reference guide, available within the help menu. So be sure to check this out to learn more about all these synopsis design, as well as Aldec's additional design constraints, which will help improve your overall linting results. And of course, thanks for watching.